You ever really stop and think about what's going on when you click a link? I mean, it's instant, right? It feels like actual magic. But in that split second, there's this wild, globe-spanning journey that's taking place. So today, we're going to pull back the curtain and see how the trick is done.
So yeah, you click a link and boom, the web page just appears. We do this all day, every day without a second thought. But what is really going on in that little sliver of time between your click and the page loading? That's the big question, isn't it? And trust me, it's this incredible, invisible dance between languages, packages, and literal pulses of light.
All right, let's get into it. The very first move in this dance is your web browser. It has to, ask for the web page. It can't just take it. So it puts together a message, a kind of formal request, using the universal language of the internet.
And that language? It's called HTTP, which stands for Hypertext Transfer Protocol. Now just think of HTTP as the official rulebook for how your browser and a website server are allowed to talk to each other. It's the protocol that makes sure everything gets delivered. We're talking HTML files, images, videos, literally everything you see online. So in this whole conversation, you've got two main players. Your browser? That's the HTTP client. It's the one that's always asking for stuff. And the website's computer? That's the HTTP server. Its whole job is just to listen for those requests and hand over whatever's being asked for. It's a really simple but super effective partnership.
Okay, so the browser has written its request, but you can't just, shout it out into the internet. It has to be prepared for the trip. Think of it like sending a package. You need to put it in a box, write an address on it, and make sure it's sealed up tight so it gets there in one piece.
And that's exactly where something called the TCP/IP model comes into play. It's basically the internet's super efficient post office. It's a set of rules, or layers, and each layer wraps your request in another layer of information, getting it ready for its big journey.
So let's quickly walk through how this works. First up, the application layer is where our HTTP request is born. But a whole web page request is way too big to send at once. So the next layer, the transport layer, chops it up into these little bite-sized pieces called packets. Then the internet layer slaps a destination IP address on each and every packet. That's the mailing address. And finally, the network access layer takes those digital packets and turns them into actual physical signals. We're talking electrical pulses or tiny flashes of light, so they can physically travel across wires and airwaves.
But hang on a second. There's a problem here, right? I just said the packets need an IP address, which is just a long string of numbers. But you and I, we don't type in numbers, we type in names, like Google.com. So how on earth does the computer figure out the number it needs from the name we give it?
Well, it uses something called the Domain Name System, or DNS for short. And honestly, the best way to think about DNS is as the internet's gigantic shared phone book. Its one and only job is to take that human-friendly name you typed in and look up the machine-friendly IP address that goes with it. I mean, can you imagine if we had to memorize IP addresses for every website? No way. DNS saves us from that. And the way this lookup works is actually pretty cool. The system kind of reads the address backwards. It starts with the most general part, like the .edu, and asks a top-level server, hey, who's in charge of this? Then it gets a referral, and it asks the next server down the line, and so on, narrowing it down until it finds the exact IP address it needs. It's this super fast chain of command that happens in, like, the blink of an eye.
Okay, so our request is all packaged up, and it's got the right address. Now for the really amazing part, the actual physical journey. This is where the digital stuff we've been talking about hits the real world, and it is seriously impressive.
So the journey always starts small, right in your home or office. Your request zips from your laptop or phone over to your router. If you're on Wi-Fi, it's traveling as radio waves. If you're plugged in, it's tiny electrical signals in a cable. Think of this as the on-ramp to the massive global information superhighway. And once it's on that highway, wow, your little request gets converted into a pulse of light. It then joins billions of other light pulses racing through these huge fiber optic cables that are the true backbone of the internet. We're talking about cables stretching across entire continents and laid on the bottom of oceans, all carrying our data at pretty much the speed of light. It's absolutely mind-blowing.
So, after zipping across thousands of miles in just milliseconds, our little data packet finally arrives at its destination, the web server. Now it's the server's turn to act. It needs to figure out what was asked for and send something back. But, the way servers do this today is way different and way smarter than how they used to.
The basic idea is simple enough. The server gets the HTTP request, it finds the resource you asked for,
Could be the main web page, an image, whatever, and then it packages all that data into an HTTP response to send right back to you. But here's where things get really interesting. This is a crucial upgrade that made the web what it is today. The original version, HTTP 1.0, was, well, it was polite, but incredibly inefficient. Imagine making a phone call, asking for one thing, getting it, and then hanging up. Then calling back for the next thing, and hanging up again, over and over. For a modern web page with tons of images and files, that's a total nightmare. So then came the upgrade, HTTP 1.1. This changed the game completely. It introduced persistent connections, which is like keeping the phone line open to ask for a bunch of files all at once. It also added something called pipelining, which let the browser send a whole flood of requests without even waiting for the first answer. These tweaks basically turned a slow, single-lane country road into a multi-lane superhighway. This is a huge reason why the web feels so lightning fast today.
All right, so the server has used these newer, much more efficient rules to put together its response. Now it's time for the return trip. And you can probably guess what that looks like. It's basically everything we just talked about, just happening in reverse.
So those packets of website data start racing back across the globe through the exact same undersea cables and routers. They find their way back to your local network, and then bam, they hit your computer. Your browser is waiting, and it grabs all these packets, unwraps all those layers we added earlier, and puts the puzzle back together, assembling the complete web page right there on your screen.
So let's just do a super quick recap of this whole amazing journey. 1. Your browser sends a request. 2. That request gets packaged up for travel. 3. DNS plays phone book and finds the right IP address. 4. The request physically travels across the world. 5. The server sends back a response using a much smarter protocol. And 6. Your browser catches it all and builds the page. It's like this perfectly choreographed high-speed ballet happening behind the scenes.
And here's the kicker. This whole round trip, this incredibly complex dance across the entire planet and back again, it happens billions upon billions of times, every single day. For every Google search, every YouTube video, every single click you make.
And it all happens so unbelievably fast that it feels, well, it feels perfect, seamless, almost unbreakable, right? But what we've just seen is that it's actually a massive chain of countless tiny individual steps, and every single one of those steps has to work perfectly. Which leaves us with a final question to think about. What happens when just one tiny link in that chain